Yeah, for context, this is some guidance on like where the rubber meets the road, how to integrate compact block filters into your app. And so for background context, in case people don't know, and I find that many developers have an idea of what compact block filters are, but maybe not the full picture of how the protocol actually works. So yeah, block filters are a way for a light client to query if they should be interested in a block without actually having to download the entire block. So these filters are often orders of magnitude smaller, and they're basically a compressed representation of what scripts are actually in a block. And you can use these to determine, should I download a block or not, to update my balance and transaction history. And these filters and blocks are served by full archival nodes on the Bitcoin peer-to-peer network. So these are real Bitcoin nodes that have a special configuration that essentially serves this data to light clients. So oftentimes this is where people start to get a little fuzzy or confused, but these are actually nodes that, or what I mean by nodes is that they're just any old computer running the Bitcoin Core software or whatever implementation you're using, and they just have this special ability to give you these compact block filters. And so because of that, a light client, at least in the context of compact block filters, must actually implement a subset of the Bitcoin peer-to-peer messages. So basically the light client and the full node have to be speaking the same language, so to speak. So this isn't something like JSON RPC or HTTPS or whatever. This is actually a separate protocol that defines the Bitcoin peer-to-peer protocol. And so along with that, you have to maintain a list of potential peers. Like, how am I going to find these full nodes that are actually going to serve this data? Well, there's a couple different ways. You could use DNS to initially get started. You can use just a hard-coded set of peers, or most likely, and where you're going to find most of your peers, is from gossip from other peers. So when you connect to a Bitcoin full node, they'll start to tell you about other full nodes that you can connect to. And as a side effect of how the Bitcoin protocol works, we actually have to decide what blockchain are we following? Like, what chain of block headers should we consider to be the chain of most work? Because that determines pretty much everything else that we do, like what filters do we request and what blocks do we request. And then finally, these relevant blocks actually have to get sent to the wallet implementation. And there's a lot of care in how this is done, because these blocks should be emitted in the order that the wallet is expecting, like in a chronological order. So yeah, that's the responsibility of the light client. And so just to harp on, like, why is this interesting? Why do all this? The light client user is kind of behind the anonymity set of the entire block that they're downloading. Like, the node that's giving them the block can't really determine much information about the user at all, because normally blocks are pretty full, unless they're pretty much empty. So this is interesting, especially when these blocks, they can be fetched at random from different connections. So any heuristic that might link two blocks together is also broken, because you can just fetch them from somebody else. So with a sufficient number of peers, you can just kind of randomly select who you're going to fetch blocks from. And there are many potential peers that the client may broadcast transactions to. So you can pick anyone from your address book pretty much and just say, hey, here's a transaction. I'm giving it to you. So that's basically how you send transactions using this light client, is you just gossip it to somebody or a couple of them. And new features of the peer-to-peer network are more easily integrated into the compact block filter node, because like what I said earlier, we actually have to implement a subset of the Bitcoin peer-to-peer messages. And finally, I think the most interesting, the light client can run on resource-constrained platforms, mobile, desktop, or even like a low-cost virtual private server, like, on the order of like a couple gigs of storage and, not too much RAM, and something that is just kind of always on and in the background. And we'll kind of get into that model later and why I think it's cool and people should build towards that future. But yeah, first we should do a big reality check, because I talked about all of the theoretical components. But in practice, how does this actually work? And like, how many of these full archival nodes are actually able to serve this data? So fellow developer from Spiral, Nick Johnson, he developed this cool program that's like essentially a network scraper or network crawler, and he called it a Bitcoin node census. And it makes sense because it's basically taking a census of like all of the nodes on the network, what type of features do they run and stuff like that. And that census found that around 10% of listening nodes, so this is kind of an important caveat, but 10% of listening nodes signal for compact block filter support. So that's around, roughly 1,000 or like 1,100 of these nodes. And the caveat here is like that those are the nodes that he is actually able to connect to, but the total number of nodes on running Bitcoin is probably in like the hundreds of thousands. They just aren't always open to even listening for connections at all. So at any given moment, some 1 to 10% of the network you can actually reasonably reach, and then 10% of those could actually help you. So this results in sync times mostly being determined how fast can this light client churn through its database and find some of those Goldilocks peers. And so part of the talk is I wanted to propose some potential workarounds or I guess solutions to these that would help make the light client experience better in practice. And one of those is DNS seeds. So DNS seeds, if the user is comfortable with it, can be relied on more frequently for users that really don't expect to be online all that often. So think like a mobile phone. You check your wallet once every couple weeks or a month or something if you're expecting a payment, like your paycheck. These nodes could benefit from just kind of using DNS as more of a crutch to find peers, because their phone probably isn't crawling the network that much and determining who is going to be a good peer to connect to all that often. So the reason that these seeders work so well is that they have up-to-date information of like what nodes are online and listening pretty much like in real time, because they're always running. And then the results can be filtered for nodes that are only going to help you serve compact block filters. So it essentially alleviates the entire problem, but it's at the expense that you have to kind of trust this DNS seeder. And maybe I'll show an example. Can you guys see my screen when I switch terminals?
Yep.
Cool. So I'm gonna demonstrate on Shore's DNS seed. This little prefix is how we say I'd like to only connect to nodes that are gonna use encrypted transport and also serve me compact block filters. And so when we hit this endpoint, we see that we basically have like 15 peers right off the bat that we could potentially connect to and should service the data that we're after if we're able to connect to them. So you can see it definitely works as a solution, but it's again, at the expense of kind of having to trust this DNS seeder is not going to give you bullshit, essentially. And so that kind of leads into the next point of wallet developers, if they really are, fixated on providing the best user experience, which I think they should be, well, they can kind of run their own DNS seeder because presumably their users are trusting them with many other things. If they're in fact the wallet implementation, so they can run an endpoint and hit that endpoint to kind of speed up the syncing process. And it should be noted that not every peer for the connection has to be one of these DNS peers. So like a nice healthy approach would be like maybe configure the node with like a couple of these or like add a couple of these peers and then use the peer-to-peer network for the rest. And that should be a pretty robust, but also like speed up the syncing process. So that is one such approach. I'm going to skip to the last bullet point real quick. Just more people can run nodes that serve compact block filters. I would argue that this isn't like too great of a solution because the incentives are relatively low for full archival node runners to essentially add more data that they have to serve and add more bandwidth. But if they're feeling very generous, this is obviously still encouraged. So this would also help alleviate the problem. And it should be noted that I think there's work in Bitcoin Core to use the block filters as a way to index the wallet faster. So it could have end benefits for the node runner as well to use compact block filters. And then it's just a matter of serving them. And a bullet point I also missed was many nodes are just not listening for connections. And sometimes this just comes down to network, your internet service provider not letting connections through. So oftentimes you do have to manually open up your Bitcoin port, to let traffic through. And I think maybe some of the node in the box solutions like Umbrel or something already do this, but I think out of the box, it's not entirely intuitive how this works. And to be quite honest with you, I'm not even sure how it works, but I do know when you run Bitcoin Core out of the box on your home internet, you probably won't be getting inbound connections passed through to you by your modem or like by your internet service provider. So something to keep in mind there. And then I think kind of the most interesting or kind of new model that we could see for this type of client would be something that's just always on. And that way it's always kind of crawling and looking for peers and it's always looking for connections. And the way this would work is the user from their desktop or maybe some more pretty interface on their phone can essentially securely sign on to this always on server and just instantly get their wallet balance and everything, transaction history, because the node is just always on running and updating information. And so when you log on, you just see the most recent state of that. And I think this model alleviates I think a lot of pain points that people might have with this sort of light client model. It reduces the sync speed to essentially how fast you can connect to the remote server because it's just constantly running. And then it also alleviates this struggle of trying to find peers because it's always kind of doing it. Cool. And then, pivoting off of the peers topic, just another reality check that unconfirmed transactions cannot be verified as valid. So in this whole time, we've been talking about blocks, like the compact block filter. You check against it and then you decide if you want to request a block. Well, what do you do about unconfirmed transactions? And there's really not much of an elegant solution for this at all, besides maybe something you could come up with like UTXO proofs or something. But the light client doesn't maintain a list of UTXOs. So there's no notion of if an unconfirmed transaction is in fact valid. like in all probability right now, yeah, if you see something where you have some outputs in that transaction and it's floating around the mempool, it's probably valid, but that's not to say it can't be invalid in the future, and people could start like flooding with essentially invalid transactions that try and make it look like you have money that you don't. It's just one of those things that the light client really can't do much about, where in the trusted server setup, you're already trusting the server for a bunch of other things, so you might as well trust that your unconfirmed transaction is in fact valid. So just another thing to consider. Yeah, now switching gears. So we have like the theoretical, and then I talked a bit about in practice, what are the struggles. Now let's see how to kind of tailor towards platforms, I think, in the best way, I guess, in a way that takes advantage of what modern mobile phones and operating systems have to offer. So yeah, the modern mobile OS is very robust. iOS itself offers a native way to schedule background tasks. These are tasks that run while your app is not necessarily open, or any apps for that matter. Your phone is an operating system just like everything else, or it runs an operating system just like your laptop or a server. And so it schedules tasks that run in the background while the user may not be aware of it. Just like how your weather app is up to date, even though you weren't opening the weather app, it periodically updates the weather. So while using compact block filters as a product, a byproduct of having to download all of these filters and blocks, it can be bandwidth and battery intensive for a short period. But there is no reason that we can't schedule some syncs at ideal times where the OS would be able to knock these out with no problem. And that would be when the phone is on Wi-Fi and connected to a charger. And another thing to note, since this paradigm is shifting from, I guess, a script-based approach where you query a server for a script, and once you query enough scripts and no transactions are found for it, then you stop. This is you query blocks, and since most blocks are going to be irrelevant to the user, especially if they haven't opened the app, there's no reason you can't just kind of sync some blocks that you don't really expect the user to have any transactions in, like overnight. And then that way the phone is just kind of constantly idling and keeping up with the blockchain. So I was going to do a short kind of Swift snippet example of like how this actually works. So something we all know and love, just like an init function, main, whatever type of thing. Like, hey, this is when the app starts. We're going to do a couple things. On Swift, in the particular implementation that I did, I just said, hey, first register any background tasks with the OS that we'd like to run, and then actually schedule those tasks to run later. And so the handle background sync function is this function we'll never actually see, but just you can imagine it starts a light client with some wallet information and fetches blocks for a wallet, and then updates the wallet at the end. So you can just imagine this as a little sync function. So we're going to use this background task scheduler from Apple and say, please register some background task name, and when you see something with this name, this is the function I'd like you to do. Just handle the background sync. Then once we're done with that, then we actually just need to schedule it. And so the cool thing about iOS, and I'm sure there's like an Android version of this, is you can, for the processing task, you can actually say, hey, I need you to have external power when you run this. And I also need you to require some network connectivity. So I'd like you to not use data, cellular data, and I'd like you to be connected to power. So if neither of those, or if both of those conditions are not met, then this just will not run, which is what we want. We don't want to be just like hammering the user's phone with bandwidth over cellular data or like nuke their battery. So a good time to do that would probably be at around like 3 a.m. Like, unless it's like a really crazy night, you're probably going to be asleep, and your phone's going to be plugged in, and you'll hopefully be connected to Wi-Fi. So we go ahead and just schedule that, and we submit this request. And then if the OS is able to complete it, like if you're connected to network connectivity and power, we'll go ahead and run that earlier handle background sync. So I kind of just want to throw that out there and just instill or like stoke the fire of like, get creative with how the user experience like that you bring to your users. And I think the whole idea of Bitcoin is to be your own bank, right? And your banking app is pretty much always refreshed when you open it. So I think having that mindset and trying to have strategies to get feature parity with a bank for your Bitcoin wallet is like a really cool and interesting design space. And in the context of compact block filters, it actually shouldn't be too crazy difficult because, like I said, most of the time this user, when they're asleep, they're not going to be expecting a payment unless it's like their paycheck or something. And we can just kind of do this background sync while their phone is connected to a charger and the internet. But yeah, some more broader like user interface considerations. The number of peers a light client might be connected to can change at a given moment. It's not like a server where it's like, oh, did we connect to the server or not? It's like you have a bunch of kind of different servers, and whether or not you are syncing or not kind of depends on, well, are we sufficiently connected to enough nodes for us to get this data? So I think just having some sort of icon or something that displays your network connectivity is super crucial for the user, because otherwise it's going to look like the app is just kind of hanging there and not doing anything. And I think Phoenix does a pretty good job of this, even though they just use typically like an Electrum server by default. It still lets you know like, hey, you're either like not connected to the server or you are. And then also another thing is like a progress bar, right? So the number of filters that you need to check should be known once you sync your block header chain. You should know like, okay, I last opened my app at block 800,000. Now the chain is at 810,000, so I have like 10,000 filters to check. So like conveying that information to the user is very important as well, because then it can give them a gauge of like, oh, I should go get like a cup of coffee, or like my sync is going to be done imminently and I can do whatever I wanted to do with my wallet. Another thing, recover wallets with logic. I think this one is just one of those things that I have a strong opinion of, because I think the inclination is for people like, oh, I'll just sync from Genesis and I don't need to make any special exceptions. When I'm doing my sync, I can just sync from the wallet chain tip, which would be Genesis. And I want to just kind of push back on that. Like, for your users, there's no real reason, if you're starting a recovery, like a user recovers their seed phrase on your app, if they're recovering a SegWit wallet, you don't need to check for anything pre-SegWit, because it was anyone can spend, and undoubtedly if they had a transaction that matched their script, it would have been spent. So yeah, if you have like a Taproot only wallet, then start your sync from Taproot. And along this line, kind of forgot to put it in, but any date or like any information you can get from your user about recovering the wallet can also speed up the syncing process quite a bit. Even if they just like take a guess, if you're like, do you know when you made this wallet? They're like, it might have been like 2021 or something. You can just say, okay, we'll start from 2020 and just scan everything up. But at least you've skipped like, I don't know, 3 years of like Segwit activation or something like that. So yeah, just wanted to point that one out there. And some more fun things I think to consider with the light client, that new blocks are just like instantly gossip to the node. So you can have really fun and like reactive user interfaces, like when a new block comes in or you check a filter or something like that. You can really make for some snappy UI components because the node is updating in real time. And then I really want to see, because I'll probably end up making it myself at some point, but I'd like to see also an app for like power users, probably something along the lines of this like VPS style, private server style, where you can like SSH into your wallet and then look at all the logs and stuff like that. My implementation itself, Kyoto, has a lot of logs and warnings and info messages that can be made useful, and more being added pretty much in every release. Kind of back to the new blocks thing, nodes emit information in real time, so can lead to some snappy UIs. So some new designs for wallets. Again, just to like set the stage, you could look for like, just Google like cheap VPS, $1 a month VPS. And these machines are pretty low spec. Obviously, they have like maybe 2 to 4 gigs of storage and a little bit of RAM. But the nice thing about this protocol is that's really all you need. You just need to be able to sort of fit one block in memory at a time, which is around a megabyte. So as long as you're below, and then of course there's like program runtime overhead and stuff as well. So as long as you're under a certain threshold, like 50 megabytes or something, you should be fine. And oftentimes these servers definitely have maybe like up to like a gig of memory. So really cheap hardware can run this protocol, and I think it would be super cool to see something that even for non-technical users, instead of trying to do everything on the device itself, to have some sort of authentication protocol and do things remotely in something that's always on and always updating. And in that sense, you get to run your own server. There's no reason you can't self-host it. You get to always have constant wallet updates because your server is just always running. And so that way you kind of get this parity with like a typical modern banking app, but instead you can self-host it and it's super cheap. And most people should be able to afford like $1 a month to essentially keep their wallet online. So this use case really inspires me. I know that it's not going to be for everybody, and I also think the use case on the phone is super cool. But I just wanted to throw out, in the future, this might be what light clients look like, especially as hardware gets cheaper. If you can run your own little bank for like 50 cents and self-host it, I think that would be super cool. But yeah, of course, since it can run on those shitty VPSs, it can also run on your phone and on your desktop. So those apps are definitely cool as well. And I guess this is the last slide. So I just wanted to throw in there, like, what am I doing for future work? And I only have one bullet point because I would consider the light client that I made pretty much feature complete. So the last little loose end I wanted to try to tackle is like using the last end blocks towards the tip of the chain as data for fee estimation, and behind that there's a lot of things that need to go on under the hood. So it's no easy feat, but I think it would be super nice to just close the loop and get the most out of the light client experience as possible, because another one would be having at least semi-accurate fee estimation would be nice for on-chain wallets. And then here I added some resources, and these slides will be under the reference implementation in the docs folder. So if this topic interests you at all, and like some of the work that we've done with BDK on kind of making these design goals a reality. I have this fork of the BDK Swift example wallet, but there's another fork on the actual BDK Swift example wallet that's really exciting for me that integrates this. There's some fee estimation research to basically justify using the last n blocks as a fee estimator. There's a Rust integration in BDK, and also the mobile bindings. And I should say also Python bindings as well, because of course there's the Bitcoin Safe project that uses the Python bindings that I hope will also be able to integrate. So yeah, that's pretty much it. I'll leave it up for questions now. Yeah, thanks guys for listening in.
Hey Rob, do you want to talk about silent payment integration? I know there's been discussions around that, and it's unclear to me, at least, the role that compact block filters could have in there. I know there's been some bips written or notes or something, but
yeah, so I think it's a really interesting area, and I think there's not really a huge reason in particular you would need to use compact block filters. Like, I know that there's a server protocol called Blindbit that instead uses this thing called like simplified UTXOs or something that is pretty much as privacy preserving, or like close to privacy preserving as compact block filters. But it's I think it's more like if you have the light client built out, then adding something like silent payments is not all that much extra work. In fact, for Kyoto, you could just use it as it is today and build the silent payments wallet on top of it. And that's what we're working on. It's just that you need to, the only auxiliary information that you need would be the, at least as I've heard them called, the key tweaks, but these are like essentially shared secret data computed between the sender and the receiver, so they each arrive at the same shared secret. As a light client, without the quote unquote like undo data, which is just the previous outputs, you can't compute this shared secret. So there needs to be a server that serves these shared secrets to light clients. But the good thing is just by serving those shared secrets, it's just like the filters. There's no way for the server to know any blocks or anything that you're interested in. They're just giving you the data. So you're trusting that the server is giving you correct data. But besides that, everything else is left to the light client to figure out, like getting the blocks and so on. So I personally haven't done a lot of work in this area yet. I do have like a little bit of a proof of concept, mostly just to get an idea for performance. It doesn't actually do any wallet stuff yet. But I think that's, again, a super exciting area for like the always on server case, especially if you think about sort of the motivation for silent payments, in that it's intended to be useful for donations and, things where you expect to more passively receive payments. So having like an always on server that's just like passively scanning for those payments is, I think, super super cool, and I'm definitely motivated to apply the VPS model to silent payments. So we will get to work on that at some point. It's just there's not enough time in the day, but that is something that I think is a really exciting area, and I think having the light client scaffolding there makes it not a bridge too far to add silent payments functionality on top. So mostly comes down to like the wallet logic, like tracking outputs and building transactions and stuff.
Thanks.
Yeah, Rob, thanks for the presentation. Quick question.
Yep.
How do we reconcile like what was being downloaded if like a disconnection from a peer happens? I know we could keep track of maybe the last one that we downloaded and just continue from there when we reconnect. Or is this even possible where there's a case of you're downloading filters and you miss maybe one or two filters, and the client actually thinks it's downloaded those filters and it continues downloading the rest. So like potentially, if you don't download those filters and you have like transactions related to them, you might not like be able to see those transactions in your wallet.
Mm-hmm.
So is there like any form of like validation, to just make sure that everything is on track if,
Mm-hmm.
whether or not there's a drop in connection or something?
Yeah. So so there's kind of two things there. For the BDK integration, all relevant blocks are emitted in order for like in chronological order, and all of the relevant blocks up to the chain tip. So the only way that you could get a wallet update is if all of the filters were checked and all of the blocks were fetched. So otherwise, it just completely fails, and you have to start from wherever you last left off. So like last month or last week or whatever. There's no like partial state for constructing the wallet update, as was done for our integration. As far as the reference implementation, you bring up some good points, and I've kept, I taken a lot of care and kind of the internal state machine and asserting that all of the filters are checked. Basically, the chain management stuff has really nothing to do with the peer-to-peer network. So if a peer drops off for whatever reason, we're able to start from whatever filter we need next, and there's no concept of like best effort, I guess. Like it'll continue to also download the filters in chronological order, so there's no like possibility of skipping them, because if somebody drops off, then the next request that we make will just pick up from where the other peer dropped off. So it doesn't, I guess the bottom line is it doesn't matter what peer is actually serving the filters. It could be 100 different peers that all dropped off and had crappy connections, or it could be a single peer. How the filters are requested is dependent on asserting that all of them are in fact requested. So that's a good point, and definitely something that I've taken a lot of care within the reference implementation to make sure everything is fetched, and that the node can advance without fetching everything.
Okay, thanks.